In this video, we're going to look at cancellation laws in rings. And what I want to do is we're going to assume that R, under its addition and multiplication, is a ring with no zero divisors. Now, what that actually means is that if we have an element that is not equal to 0, and we know that A times B is equal to 0, that's enough to force B equal to 0. And likewise, if A is not equal to 0, and we know that C times A is equal to 0, that's enough to force C equal to 0. If we put these two things together, we can basically say that if R has no zero divisors, then we have the standard fact from ordinary arithmetic that if A times B is equal to 0, then either A is equal to the 0 in the ring or B is equal to 0 in the ring. And let me indicate that this might not be regular arithmetic by putting those subscripts on the 0. Now, what I want to do is I want to investigate the situation that A times B is equal to A times C and see what we can say about that. So in other words, what we want to do now is if R is a ring with no zero divisors, and we know two things. We know that A is not equal to 0, and we know that A times B is equal to A times C. Then what else can we say? Well, what I want to do is I actually want to think about this particular equation and the fact that A is not 0 and the fact that there are no zero divisors. And we're going to put these three things together and get a remarkable and important fact. So let's look at this. AB equals AC is going to imply that A times B minus A times C is equal to the 0 element of the ring. And that's just basically subtraction. Now, we can always factor out that A, since it's on the front side of both terms, and write this as A times B minus C is equal to 0R. This is by the distributive law. Now, what I want to do at this point is I want to remember R has no zero divisors. And I also want to know that, so since R has no zero divisors, the statement A times B minus C is equal to the 0 implies A is equal to 0 or B minus C is equal to 0. Now, it turns out that we've assumed that this guy doesn't happen. So this is not true because we've already assumed that A is not equal to the 0 element. So when I realize that didn't happen, we are forced into accepting that B minus C is equal to 0. So in other words, the fact that A is not 0 and A times B minus C is equal to the 0 inside the ring, and the fact that A is not a 0 divisor, all come together and imply. So this complex statement implies that B minus C is equal to the 0 ring in the ring. But gee, that says B and C are the same thing. To do that, all we have to do is add C to both sides. Now let's actually think about what we've actually done. What we've done is we've shown that if we're in a situation where we have no 0 divisors, and we have this particular statement, and we know that A is not 0, these three things together imply that AB equals AC will give me B is equal to C, or as the other case, possibly A is equal to 0. And we can clean this statement up, and this is going to become what is known as a left cancellation law. So I want to restate this cancellation law very carefully. So a left cancellation law for rings with no 0 divisors. The left cancellation law for rings with no 0 divisors states if AB is equal to AC, then A is equal to the 0 element of the ring, or B and C are the same thing. In other words, what we can basically do informally, we can say, okay, if we know this, and we know that A is not equal to 0, we can informally cancel those two A's and conclude that B and C are the same thing. Now, I do want to make a warning. And this is coming out of the previous video. If our ring has 0 divisors, there is no left cancellation law. And it's important to remember that. Well, what I want to look at next is a right cancellation law. And again, this right cancellation law is going to be for rings with no 0 divisors. And if R is a ring with no 0 divisors, if we know that B times A is equal to C times A, then we're going to have either B is equal to C or A is equal to 0. One of those two things has to be true. Now, one thing that I want to point out is that the proof of this is going to be left as an exercise for you to complete in a quickly jot assignment. So I'm not going to talk about the proof of that. I do, however, want to talk about how cancellation works in commutative rings versus non-commutative rings. So the right cancellation law, again, just is informally saying the same thing, that we can cancel as long as the A winds up being on the right. So let's see. Informally, if we're in a ring with no 0 divisors, and we know BA is equal to CA, and we also know A is not equal to 0, then we can informally say those A's can be canceled out to get B is equal to C. So now what I want to do is look at cancellation laws in commutative versus non-commutative rings. So in a commutative ring, AB is equal to BA, AC is equal to BC, and hence AB equal AC implies B equals C, and BA equals CA implies B equals C, can also be very informally thought of as a two-sided cancellation law. And what I mean by that is if we have AB is equal to CA, then we can formally rewrite the right-hand side as AC, and then we can cancel those A's to get B is equal to C as long as A is known to not be 0. It's important to not get into the habit of doing the cancellation up here. So informally, we don't want to write, oh, cancel these two guys and get it. And the reason why is confusion, and we're going to look at that in just 1 second. So I want to kind of look now at non-commutative rings. In a non-commutative ring, there is no two-sided cancellation law. In other words, if I have AB is equal to CA, I cannot conclude that B and C are the same thing. So I cannot conclude that B and C are the same thing. And the reason why is that I do not know that CA is equal to AC. And in fact, if CA is not equal to AC, then AB is not equal to CA, and we can't cancel. So it's very important to realize that a non-commutative ring with no zero divisors, and I should add that up here, no zero divisors, we can't just willy-nilly cancel on both sides. Now, cancellation laws, there is another warning that I want to tie up with, which is I want to reiterate that if a ring has zero divisors, there are no cancellation laws. So as an example, if we're working in Z12, there are zero divisors. So in Z12, if we know that A is not 0, and we know that AB is equal to AC, we cannot conclude that B is equal to C. And so it's really important to understand that you can only use cancellation when there are no zero divisors. And that leaves us with the need to define the kind of rings that have no zero divisors. So to wrap this up, we wrap it up with a formal definition. Let R under its addition and times be a ring with no zero divisors. Then we call R a domain. So the word domain means no zero divisors. So domain equals no zero divisors. As an easy example of a domain, the integers under their ordinary arithmetic is a domain, because inside the integers we do know that if a times b is equal to 0, that will force a equal to 0 or b equal to 0. And so inside z, there are no zero divisors. And so to finally wrap things up, I want to restate the important result that we have shown. If R under its arithmetic is a domain, then we have both a right and a left cancellation law.